So this is a subject that goes back a long way, really, to the roots of commutative algebra in invariant theory. Most of you know the history quite well, or at least many of you do. But nevertheless, I thought I would begin by telling you what you might have learned in a first-year graduate algebra class, since that's sort of the right place to start this. Of course, the story starts with Hilbert's proof of the finite generation of the ring of invariance of a reductive algebraic group in the late 19th century. That's the thing that made Hilbert Hilbert, that made Hilbert famous at that time. It was his first big theorem. He was quite a young man, and he was interested in all aspects of this. The one that concerns us here is the question of counting invariance. So, let's see, there's chalk. Hilbert showed, of course, this is prehistory, that if you have a polynomial ring, let's see, I'll have standard notation. S will be the polynomial ring over a field K, which I can barely refrain from calling C, in X0 up to XR. And I'll write a script M for the maximal ideal, the homogeneous maximal ideal, X0 up to XR. And I'll always think of graded things, graded modules, graded rings, graded homomorphic images of this. And then this prehistory is that Hilbert looked at rings of invariance, things like that, and proved that they were finitely generated by forms of various degrees. He then wrote that sensibly as a homomorphic image of some other polynomial ring whose variables have different degrees, y1 up to yt. And he proved, by a method that I'll show you in a second, that the number of invariants of degree d, the number of independent invariants of degree d, by which he meant the degree d component of this graded object, is eventually a polynomial function of d, well, a polynomial with periodic coefficients, or more interestingly, he wrote down an actual formula for it in terms of some binomial coefficients. So that's the dimensions of this. Now, that's the prehistory. I want to look at this in a different situation. I want to look at the case where the y's have the same degree, let's say 1. So I'll change my notation and go back to thinking about S and homomorphic images of S. And I want to think of that as a way of getting invariance of projective varieties. Now, we heard from Karen the other day, very elegantly put, that people study families of projective varieties. This is not some wild aberration of the moderns in algebraic geometry. It goes back to the fact that you can write a plane curve as f equals 0, and then you can let the coefficients of f vary, and that's a kind of natural family of varieties. And all the talk about families of varieties since then is a kind of abstraction of the good properties of that example. So, in general, if we look at a variety, I'll think of a homogeneous coordinate ring. So x in PR corresponds to Sx, which will be that polynomial ring there, mod the ideal of x. And these are, again, homogeneous. And a family of varieties would be something like a variety in PR cross some affine space AS, and I think of it as Sx is S with some more variables adjoined for the new affine space, S of T1 up to Ts, mod some ideal I. And then, as Karen told us, x for some point P over there would be just Sx, well, would correspond somehow to Sx mod the maximal ideal of P in these variables. So let's say Sx with the T's equal to T of P. Right, so we take the fibers of the projection of this to AS, and those are the XTs. Now, in our original situation, so if I write Sx I guess I should have used a different letter, shouldn't I? So let me put a script letter here, not to confuse us too much. So again, if I write Sx, I can write the function expressing the number of independent functions on x of degree d, so to speak, hsx, the Hilbert function of d, that's the dimension over k of the degree d part of Sx. And Hilbert's theorem, which I'll prove for you in a moment, is that hsx of d is equal, for d sufficiently large, to p x of d, a polynomial. And of course, the algebraic geometers recognize this polynomial as chi of ox of d. And the family up there is flat in the situation I've written it, or even over any reduced base. X is flat. Those are the families that Karen told us were the good families, if and only if this p x sub p, as I've written it there, of d is constantly equal to some polynomial p of d. It doesn't depend on the point little p. So somehow this Hilbert polynomial is the invariant. It's not just a sort of arbitrary collection of numbers that you might make out of a projective variety and then think, is that interesting? It is the invariant which tells you whether families are flat. It's the thing that tells you that varieties belong together. Now, from an algebraist point of view, we might ask a different question. We might ask when this family of rings that I've defined, really, by this object is a ring, right? And I get a new ring for every point p. You might ask when that's flat. And that's flat if and only if the Hilbert function is a constant. So theorem, the family S xp is flat if and only if h Sx of d is constant. So from this point of view, it's rather natural to try to look at what this Hilbert function is and what it means, and try also, since flat families are still rather large and contain varieties with all kinds of different properties, it's rather interesting to ask what the properties of individual ones are. In other words, can we find some invariants which strictly refine this Hilbert function? And the invariants that I want to talk about are exactly of that kind. So we should think of them as a way of refining the Hilbert function. So let me back up now and prove that the Hilbert function is eventually a polynomial using Hilbert's original proof, and that will take us to the invariants that I want to study. So theorem M, let's say it's a direct sum of M sub d, a graded module, I'll stick with this notation forever. Then if M is finitely generated, then the Hilbert function hm of d, that's by definition the dimension over the field of M sub d, is polynomial for large d. That's the way this is usually stated, but actually the theorem that you always prove is much stronger, or at least the theorem that you prove the way I'm going to prove it, and it gives an actual closed form version of the function itself, from which you see immediately that it's a polynomial for large d. So polynomial for large d, let's say, and more. We'll see that in a moment. So how do you prove it? Well, Hilbert's idea, this is not the proof that's in lots of modern textbooks. Hilbert's idea was to compare M with a free module. So let's think first about the free module. What is the Hilbert function of a free module? Well, of course, the free module is a direct sum of rank 1 free modules, so you might as well think about the rank 1 case and then add them up. So how about a rank 1 free module? There are more of those than you might think in this situation because we're looking at graded modules. So you have to distinguish the rank 1 free modules by what degree their generator is in. Otherwise, of course, they're all the same. So I will write S of minus A for the rank 1 free module with generator in degree plus A. What an awkward choice of notation, right? But it's justified by the general formula M of B in degree D is equal to M in degree B plus D. So if you think about this formula, you'll see that this is the right notation. Okay, and let's write down the Hilbert function of this module, HM. Well, of course, it's just the translation by A of the Hilbert function of S. So we might as well write down the Hilbert function for A equals 0 first. HS of D. All right, so how many monomials are there in degree D in a polynomial ring with R plus 1 variables? Well, if you line up the factors and sort them by increasing index, then you get a weakly decreasing sequence in degree D of D numbers less than or equal to R, right, between 0 and R. And now if you add I to the ith one, then you get a strictly increasing sequence of numbers less than or equal to R plus D. Actually, R, and there are R plus 1 plus D choices of the index because I started with 0. So we have D things chosen from R plus D plus 1. Somehow I got an extra 1 in there. Where did it come from? Oh, I added 1 to the... That's right, I added 1 to the first one. So the 0 has become a 1. So this is R plus D choose D or choose R. It doesn't make any difference. Okay? So there's the Hilbert function of S. So the Hilbert function of S of minus A is then just by translation R plus D minus A choose R. And what is this function? Of course, this is R plus D times R plus D minus 1 times R plus D minus 2. R factors all divided by R factorial. That's a polynomial of degree R, because there were R factors in D. Except it's not, because when D is less than R, you're supposed to think this is 0. And it's 0 for all D less than R, infinitely many values. So this is certainly not a polynomial function, but it is a polynomial function as soon as D is bigger than, I guess, minus R. It's a polynomial function for large D in any case. So that's exactly the content of, that's why this isn't a polynomial function in general. That's why it is a polynomial function for large D. That's the whole mystery there. So we could do this now for the direct sum. I won't even bother to write it down. It's just that you add these up. And now we have to compare an arbitrary module with a free module. And Hilbert did that by taking a free resolution. So here's M. Choose a set of generators for M of, yeah.
Why can R plus D be less than 0? Because R is the number of variables, isn't it? And D is the dimension. I don't see why it would be less than 0.
I'm sorry, I didn't understand the question.
Well, you were talking about D.
This is a polynomial function. It happens that the polynomial which is equal to this for large D happens to be equal to 0 for a certain number of steps, for a certain number of integer values starting from 0. Think about this. This is R plus D times R plus D minus 1, etc. Right. So if R plus D is greater than or equal to 0, then I have a 0 factor on top. So this is 0. So it actually agrees with the real Hilbert function as long as r plus d is bigger than or equal to 0. Then they just are different.
Yeah, well,
That's an accident of combinatorics.
Well, my question was, why would r plus d not be greater than 0? Because r is the number of variables.
True. And d is the degree. But no, d is the degree. The degrees could be negative. I could be looking in negative degrees.
Okay.
Right? Well, nothing there, but I could look anyway. It's just convenient to keep that clear and separate. So I take some generators for m in degrees, let's say a I know what's coming, so I'll write them as degrees a0j for varying j, and write here the direct sum s of minus a0j, and think of this as the 0th approximation to m. It's a free module. I'll call it f0. And then Hilbert, exactly for this purpose, proved the Hilbert basis theorem, which said that the kernel of this map, like any other submodule of a finitely generated module, would be finitely generated. So I can repeat the process, choose generators at the next stage, and therefore map a free module onto the kernel, s of minus a1j, summed over j. Call this f1. And since this free module maps onto the kernel of this map, this is an exact sequence. And now I can continue the process merrily until I get tired of it, right? But the great thing is that Hilbert showed that if you do this, after a while, the kernel is itself a free module. That's a kind of magical fact about polynomial rings. What gets better? So why is this image better than this module? Well, you might say it's a submodule of a free module. That's better than an arbitrary module. And that idea can be extended somehow to explain what might be getting better and why this ends. I won't bother with that. But in any case, Hilbert showed that after a while you can stop and you get a free module, f t, let's say, sum over j, s of minus t, a sub tj. There's some dots in here. And that t can always be taken, that is to say, the kernel will become free. No matter how you choose these generators, no matter what you do, the kernel will become free before you get to t equals r plus 1. This is Hilbert's Syzygy theorem. And as I say, it wasn't proved for fun. It was proved for this application to show that Hilbert functions were nice. So let's harvest the result of that, which is that the Hilbert function of m is then the alternating sum, because if you pick out the degree d part of this sequence, it's just a sequence of vector spaces where you take the degree d part of each of these terms. And in an exact sequence of vector spaces, the alternating sum of the ranks is 0. So you can use that to compute the this rank as the alternating sum of the others. And I'm about to write that down. Minus 1 to the I. Well, let's see. It's really going to be here the Hilbert function of fi. But I can write that as the sum over j of the Hilbert function of s of minus aij. And I've already written that as r plus d minus aij, choose r. Right, and this is a finite sum from 0 to t. And so for large d, this will certainly become polynomial. And you can even sort of see what d you have to take, or what d at least you can be sure if you take, namely d has to be bigger than any of the r minus aij's. And if you think that smacks slightly of the regularity that we heard about yesterday in group cohomology, it does. It's very closely related. And Jessica Sidman's talk tomorrow, is Jessica actually here somewhere? There she is. Will explain a little bit more of the relation, I think, between where the function becomes a polynomial and these numbers aij. I might get to that later today. So there's the formula written in a nutshell. And now we see that the Aij are a priori a refinement of the Hilbert function. If you have constant Aij's, then you have constant Hilbert function. Before I go on, let me introduce a different terminology for the Aij's. Somehow there might be many Aij's the same, and it's convenient to collect them and count them. So let me write instead Fi as the sum, again you could think of it over j, but it's a different j, of s of minus j to the beta ij. So beta ij is the number, sorry about the coincidence of j's, the number of aij equal to j. But you have to disentangle the j's. Those are different j's. Yes?
Are you going to say something about the meaning and introduction of the word syzygy?
Syzygy. I wasn't, but it's from the Greek, which means yoking together of oxen. It was used early in history and astronomy for the relation between planets in a line. And I think Cayley introduced it in this context as a relation between polynomials.
So it's things lining up just right?
It's things lining up just right. That's right. Exactly. Oxen, first of all. We haven't seen a syzygy yet, but we will in a moment. So anyway, I have the beta ij's here, and I'll call these beta ij's the graded Betti numbers. This is by analogy with the topological situation. We have a chain complex, and these really are Betti numbers. But we'll see that that's more than analogy if I get there today. One can write down lots of examples which come from chain complexes, indeed. So there they are, and let me rewrite this formula in those terms for future reference. It's the sum minus 1 to the I of sum over j of beta ij times r plus d minus j, choose r. Okay? So there's our Hilbert function written in terms of the graded Betti numbers. Okay, so my thesis is that the graded Betti numbers contain more information than the Hilbert function. Hilbert function, remember, is telling us about flatness. The graded Betti numbers, therefore, refine flat families. They stratify flat families. Now, there's a lot of need for stratifying flat families. Flat families, first of all, if you look at all varieties in projective space with a given Hilbert function, let's say, whose homogeneous coordinate rings have a given Hilbert function, you get a nice flat family. That family tends to have lots and lots of irreducible components. And they're all kinds of horrible components, and they have non-reduced points, and they're singular. All sorts of stuff is going on within that family. So it would be really nice to have a way of dividing up the family into nice small pieces. People have hoped that this was the way, and I have to tell you it's not in general. This is not nearly a fine enough refinement, for example, to pick out all the components of the Hilbert scheme. That's what I'm referring to. But it goes some distance, and there are very interesting geometric examples. And I guess algebraic geometry is, I've always felt, a subject of examples rather than a subject of theorems. It's really built around funny examples and interesting examples. So there are lots of interesting examples in which these invariants carry just the sort of geometric information that you'd like to see next after the Hilbert function, or Hilbert polynomial. Yeah.
I was going to ask you, when you said Hilbert function recently, did you mean Hilbert polynomial?
No, I meant Hilbert function. I'm talking now about flat families of rings.
Ring.
Yeah. But if you want to see them as varieties, then just take cones.
So the betas actually give you the Hilbert function.
The betas give you the Hilbert function. This is the Hilbert function that I've just computed, right? This is on the nose the Hilbert function if you interpret these binomial coefficients as combinatorial objects. And it's the Hilbert polynomial if you interpret them as polynomials, right? It's just a matter of setting lots of terms equal to 0. That's really all it is. So this is the Hilbert function. Now, I thought before I went further I should stop and do one example in which you actually see something geometric that comes out of the graded Betti numbers, because probably half of you have not seen such an example produced in the flesh. So let me pause and do that. And I guess I'm faced with the need for an eraser. So you'll see more examples of this type, and done probably in more loving detail by Jessica tomorrow. I'm going to give Jessica so many assignments by the end of this talk that, of course, she won't do them all. But this is one that I think she plans to talk about. Let's look at 4 tuples of points in the plane. So if you want to think about that as a family, since this is the beginning of something, let me really write it out as a family of 4 tuples of points. What you do is you say, well, what's the base space? The base space is the space that let's think for 4 distinct points. You can do this with 4 points, a scheme of length 4 if you're into that sort of thing. But let's think about 4 distinct points. So what's the parameter family? Well, it's just a direct product of 4 copies of P2, if I label the points anyway. And but I have to remove the diagonals. So that's the base. And what's the space in which the family lives? Well, it's P2 cross that parameter space. So in other words, I have X contained in P2 cross this funny parameter space, which is P2 cross P2 cross P2 cross P2 minus diagonals. And I'm going to call it T. And then I project to T. And the scheme that I take in here has here the 4 points that are labeled by these 4 points. Right? So that's what it is. And so I can then look, I'll write it down algebraically in a moment, at least in the flat part, the flat algebraic part. So now, first of all, you might ask, is this a flat family? Let's ask that question. And we know we only have to check the constancy of the Hilbert polynomial to see whether this is flat. Is the Hilbert polynomial constant? Well, how do you compute the Hilbert polynomial of 4 points, right? I didn't write down algebra. I'm not about to do all this stuff. How can I compute the Hilbert polynomial of 4 points? Well, let's just look at forms of degree D, and we have to think about those mod the ones vanishing at the points. So we're really thinking about the forms. If we choose homogeneous coordinates for our 4 points, then we can think about the forms as functions on the 4 points, or if you like, dehomogenize. And so we get functions of polynomial functions of degree D restricted on the plane, restricted to 4 points. And we're asking, how many independent ones are there? Now, the set of functions on 4 points is 4-dimensional, right? You could send one of the points to 1 and the rest to 0, and that's the basis. And so in order to get, so that's the maximum number of independent functions we can get. And it's pretty clear that you can interpolate to get any function like that on the 4 points as the restriction of a polynomial. Well, how could you really prove that? You just have to prove that there's a function that vanishes on any 3 and is non-zero on the 4th, which is a polynomial function of large degree. So, well, that's not very hard. Here are the points. And I take some complicated curve going through 3 of them and not going through the other one. That's a polynomial function of whatever degree it took me to do to avoid this last point, vanishing on 3 and not vanishing on the last. So I obviously get all 4 functions on the points as restrictions of polynomials. And you can ask more refined questions about that, and I think Jessica is going to talk about that tomorrow. But in any case, it's easy to see that the Hilbert function, the Hilbert polynomial, is constantly equal to the constant polynomial 4. 4 of D equals 4. right? So that's the Hilbert polynomial, constant, and therefore this is a flat family. So that's great. But still there are geometric distinctions between sets of 4 points. For instance, some sets of 4 points lie on a line. Some sets of 4 points have 3 of them on a line. Well, any with no 3 on a line is the same as any other up to projective transformation. So that's where the story sort of ends in this case. That is the natural stratification, is how many lie on a line. Because if 4 points, no 3 of them lie on a line, then after projective transformations, you can always reduce them. So if no 3 on a line, then you can write the points as, after projective transformation, up to PGL of 4. You can write the points as 1, 0, 0, 0, 1, 0, 0, 0, 1, and 1, 1, 1. Right? So there is really only one type of set of points, no 3 of which lie on a line, 4 points. However, there's this other invariant. How many lie on a line? So let's see whether we can tell what these things look like depending on that invariant. And I claim that that's exactly the invariant which shows up in the graded Betti numbers. So this is a pretty trivial example, I think you'll all agree, but nevertheless it shows that we're looking in the right direction for geometric invariance. So let's just do this. Suppose, let's first take this general case. So 4x equals 4 points. And P2 again. Case 1, no 3 on a line. Then what do they look like? Well, I said any 4 were the same as any other 4. There they are. And there you could write them. Well, you know, there's a conic through any 5 points. So there's certainly a conic through 4 points. And there's one parameter family of those things. So if you vary them a little, it sort of stands to reason that you can write it like that. Or if you don't like, if you feel that I might have cheated somehow by just drawing those 2 conics, you could also think of the 2 conics as being 2 pairs of lines. This pair of lines is one conic, Q1, and this pair of lines is the other conic, Q2. And no 3 points lying on a line is exactly what it takes for me to be able to draw that picture. Exactly. So we see from this that we can write down 2 quadratic forms without common factors. Here you see they're without common factors because one is the product of 2 linear forms this way, the other is the product of 2 linear forms this way. So 2 quadratic forms without common factors in the ideal of the points. Now, let's see what the Hilbert function really is and see whether how many quadratic forms should there be vanishing on this. So Sx, in this case, let me write H sub Sx of D as a table. So here's D. D equals 0. How many constant functions are there that vanish on the 4 points? None. Right? So mod the constant functions that vanish on the points, there's one constant function, and therefore I get 1 as the value of my Hilbert function. Linear forms vanishing on the points. Well, if no 3 lie on a line, then of course there are no linear forms vanishing on the points. So there are 3 linear forms on P2, so I get 3. Quadratic forms. Well, once again, I have to say, are there, can we get every polynomial function, all 4 polynomial functions, by looking at quadratic forms restricted to these 4 points? And it's pretty obvious that we could move a couple of these lines to miss any one of the points, and therefore I get all 4 quadratic functions, and it's the same argument applies to higher degrees. So the Hilbert function has become a polynomial at this step, and it is equal to 4, 4, 4 forever after. Okay, so there's the Hilbert function. Now there's a 6-dimensional family of quadratic forms in 3 variables. 2 plus, yes. So if there are 4 left over after you kill the ones vanishing on the points, then there must have been a 2-dimensional family vanishing on the points, and we found it. We found 2 independent ones. How many cubic forms are there vanishing on the points? Well, let's see. So again, the number of cubic forms is r plus, this is in this case 2, plus 3. Choose 2. That's 10. There are 10 cubic forms vanishing on the points. So there are, and mod the ones vanishing, there are 4 left over. So there are 6 cubic forms in the ideal. Now, you could get 6 cubic forms by taking the 3 linear forms times Q1 and the 3 linear form times Q2, unless, of course, you got some overlap in those. Could you have gotten an overlap? Linear form times Q1 equals linear form times Q2. Well, by unique factorization, this would mean that this is linear form 1, this is linear form 2. This would mean that Q1 and Q2 have a common factor. Right? L1 can't be the same as L2, therefore it must divide Q2, and then Q2 is L1 times L1 prime. Here's a common multiple which is of degree less than the sum of the degrees, so there must be a common divisor there. So we see that as long as Q1 and Q2 have no common factor, there's no coincidence like this. So Q1 and Q2, the 2 quadratic forms in the ideal of X, generate all the cubic forms. And we could go on with this analysis in some detail and prove that they generate the whole ideal of the 4 forms. So in this case, the resolution looks like this. We have M, which is Sx. We pick a generator, 1 for that module, and map S onto Sx. We've seen that we have 2 quadratic forms which generate the ideal. So I have to pick a free module as generators in degree 2 to map onto each one of those 2 quadratic forms. And then what's the kernel of this map? Well, it should be a rank 1 module. It's pretty easy if you know some commutative algebra to show that it has to be free right away. But in any case, we can write down one relation which is obvious. If I take here Q1, Q2 to be the matrix of this map, then Q2 times Q1 is equal to Q1 times Q2. So Q2 minus Q1 is a relation. And in fact, it's not too hard to show that this is a free resolution. There's an S of minus 4 there. So the graded Betti numbers are beta, let's see, how did I notate this? Beta 0, 0 equals 1. Beta 1, 2 is equal to 2. And beta 2, 4 is equal to 1. And all the other graded Betti numbers are 0. Now, it's rather awkward to write them out this way and say all the rest are 0. It would be much more convenient to have some notation for this. And the standard way to do this, which I think is actually due to Mike Stillman, is now to write down a Betti diagram. Every subject has its own particular flavor. This subject is filled with Betti diagrams. Subjects which are filled with spectral sequences, well, suddenly you get this array of things, and the audience turns off, right? At least the audience who hasn't played with spectral sequences. Similarly, with graded Betti numbers, the audience that hasn't played with these tables a little bit tends to be put off when the algebraists begin to write down these tables of Betti numbers. So this is a place to pay special attention if you don't know this already and understand what's going on. I'm going to notate this resolution as follows. There's the Betty diagram. Now, where did those funny numbers and dashes come from? So this 1, first of all, it's written backwards. That's one of the things that annoys people right away. It's written backwards. That is to say, I wrote that resolution, as people usually do, with the arrows going from left to right. Here, the arrows, you should think of the arrows as going the other way. So the module represented by this column is S. The module represented by this column is S of minus 2 squared. And the module represented by this column is S of minus 4. In general, the columns within the table represent free modules in the resolution, and you should think of the arrows as going from right to left. Now, the things over here just are place markers. They're degrees. I could leave them out. Nothing would change. They're just the numbers from 0 to as far as I felt like counting. The numbers in the boxes are the graded Betty numbers. This one is beta 0, 0. This one is beta 1, 2. This one is beta 2, 4. Why is beta 1, 2 in the 1 row? Well, that's because the lowest degree that a map in a minimal free resolution has is 1, and therefore, when I step back, I expect the degrees to increase by 1, so I've sort of shifted to account for that. So, little digression, what is a minimal free resolution? I didn't say anything about uniqueness of these invariants, and nobody was nervous enough to ask, or maybe you're all just too well educated to ask. But, you know, if I'm going to use these beta ij's as invariants to define something, maybe they should be invariant under something. And in fact, they're not. I could have taken any free resolution to make this computation, and I could get different sets of beta ij's. But it is the case that if I always choose a minimal set of generators for m corresponding to these numbers, a minimal set of generators for the kernel corresponding to these, then the beta ij's are uniquely defined, and in fact, the resolution itself is unique up to isomorphism. Any two of these with the same minimality property would be unique. So this is actually a pretty good situation, but it's convenient to say something a little bit more. I guess I should just erase this theorem. To say something a little bit more systematic, because there's a good notion of minimality for complexes too, which can't depend on choosing minimal generators. So, little digression on minimality. Minimality. So a complex of free modules. What is a complex? It just means a sequence of free modules and maps between them. Possibly infinite. Call this phi I plus 1 and phi I. Phi I in general is the map emerging from fi. This is minimal if phi I of fi is contained in the maximal ideal times fi minus 1. This works the same for local rings. That's why I've written it this way. In this graded case, I like to think of it differently. I think of writing these phi's out as matrices, and then what this says is that no matrix has an entry of degree 0 in it. All entries of positive degree. So if entries have positive degree, then and this is really a resolution, then the generators of fi have to map onto things of degree higher than the generators of fi minus 1. And therefore, I expect the degrees that appear, the twists that appear here, to go up by at least 1 each time. So this Betty diagram takes advantage of that fact to be a little more compact than it otherwise would by putting the things of degree 1 higher in the place immediately behind a a given place. So that's why this is spread out, but let's write this out in general. So in general, I would have, if this was the one for the Sx that I had here. In general, if I had a module, I'd write my Betty diagram out by taking whatever degrees I had to. And in the row corresponding to a degree, I put down the number of summands in the free module, but corresponding to that degree shifted by the number of places back. So here goes the Betty beta 0 I. Here will go beta 0 I plus 1, and so on. What? Beta 1 I plus 1. Thank you. Gee, there are lots of awake people. That's good. So in general, you could write down what's in the ijth spot in the matrix. So that's what the Betty diagram is in this case, and I want to write them down systematically so that you sort of get used to this idea. Let me write it up here, however, so that I don't lose so much space. So it was 1, 2, 1. Oh, and the dashes, what are the dashes? The dashes are just a short way of writing 0, so that you don't have to look to see whether it was 0 or just beta written very round. So those are what the dashes are for. You never know what kind of handwriting you're going to meet. Let's see. Okay, so that was case 1, the generic case, so to speak, when all the points are spread out. Yes?
Why is it beta 2, 4 and not 2, 3 then in the third column?
So beta 2, 3 would have been here. Here's beta 1, 2. If I stepped 1 back from that, I would have a degree 3 thing. And I had to go down one more step to get beta 2, 4. Right? You can sort of see these are spaced equally in height, just as I went 0, 2, 4, as I went back in the resolution. Once you get used to looking at this picture, it's really a very convenient way of displaying information. But until you get used to it, it's just a nuisance. So that's the, that's the Betty diagram picture. And now let's go on to the next example. Suppose 3 points lie in a line. Three points on a line, one off. So the picture is ... There's the line, and there's one more point. What's the Hilbert function? Well, once again, there are no constant functions vanishing on some points, so that's easy. Therefore, modulo the ones that vanish, there's one left, one constant function. How about linear functions? Well, there are no linear functions vanishing on all 4 points. That's what we said. So again, there are 3 linear functions, mod the ones vanishing on the points. How about quadratic functions? There's the interesting place. We saw that there could be 2 quadratic functions vanishing. In fact, to vanish at a point, there's always one linear condition on a form of any degree, any point. And it's just a question of whether the conditions are independent or not. So to vanish on 4 points is always 4 linear conditions, possibly dependent. So you always have at least 2 quadratic functions vanishing. And the question is whether there are exactly 2. And to answer that question, you just have to say, is there a quadratic function which vanishes at each triple of points and is non-vanishing at the last one? Well, how about this point? Is there a quadratic function vanishing on all these 3, not vanishing on this one? Yeah, of course. Take the quadratic function to be the linear form defining the line times the linear form defining that line. Right? There's a quadratic function not vanishing at this point. How about if we wanted a quadratic function not vanishing here but vanishing at all the others? Well, again, no problem. Take those 2 lines, and their product is a quadratic function that vanishes at these 3 points, but not at this one. Right? So yes, the 4 points impose independent conditions on quadrics in this sense, and therefore the Hilbert function is again 4 here. Now, it's a trivial exercise. Please think about it if you don't know it already, that once you hit the Hilbert function, in this case, Hilbert polynomial, you'll stay there forever. If 4 points impose independent conditions on quadrics than they do on cubics too. Hint, just add a line far away from the whole picture to see the story. And so we get 4 forever. And what you see is that the Hilbert function is the same as in that picture. So here's an example of a flat family of SX's. Remember, the family of all sets of 4 points was flat. And we see that still you can it's still flat if you look at homogeneous coordinate rings. The family of homogeneous coordinate rings is flat, at least as long as the 4 points don't lie on a line. If the 4 points did lie on a line, by the way, let me put that case up in parallel. Four points on a line. So then Hilbert function HSX. Well, there are still no forms of degree 0 vanishing on the 4 points, but now there is a form of degree 1 vanishing on the 4 points. That was the whole point of having them on a line. So in 1, I have a 2 here. Lord alone knows what comes next. Well, are there quadratic functions vanishing at 2 but not, at 3 but not 4? No, there aren't, right? Because any quadric through 4 points meets this line 4 times, contains the line. So any quadric vanishing at 3 of these points still meets the line 3 times, contains the line, vanishes at the 4th. So again, the conditions imposed are dependent, and instead of getting a 4, we get a 3. And then from cubics on, you can easily see that you get 4. So the Hilbert function is quite different here. And so the family of SX is not flat when you take all sets of 4 points, but it is flat when you take 4 points, not all on a line. So this is a flat family. And what I want to prove in the next 3 minutes is that, in fact, the Betti numbers change. So the Betti numbers successfully tell you the remaining bit of data about the homogeneous coordinate ring, namely whether or not 3 points lie on a line in this flat family. Okay, so what are the Betti numbers? Let's see if we can figure out the equations. There's a convenient way of writing them down. There are actually various ways. Let's look for the 2 quadrics. We know that there have to be exactly 2 quadratic forms vanishing on the points. And so let's look for them for a starter. So here are the points. And I'll write the first quadratic function. Whoops, there's one more point. In orange. So here's a quadratic. Well, any quadratic function vanishing on these 3 points meets this line 3 times, and therefore has to contain the line. So any quadratic function contains the line. And if you want one that vanishes at the 4 points, you can add another line, any line, through the 4th point. So there's a quadric vanishing on the 4 points. And I had some notation for this. So let's call this line A and this line B1. Now, if I want another quadric vanishing on the 4 points, then I can take purple chalk and draw it like this. I'll just draw any other line through the last 4 points. So there are 2 quadrics vanishing on the 4 points. And we know they're exactly a 2-dimensional family of quadrics because we computed the Hilbert function already. So these span the quadrics vanishing on the 4 points. What about cubic forms? Last time we multiplied the 2 quadrics each by 3 linear forms, and we got 6 cubic forms. Unfortunately, if you multiply, so the two quadrics are now, I didn't name the other line. Can you actually see this purple chalk in the back? Bet you can't. Chris, you're a brave fellow. Can you see this chalk? No. Okay. Let me change to white then. Ah, B2. Thank you. So the two quadrics that I have so far are A, B1 and A, B2. And A and B are linear forms. Now, if I multiply these by 3 linear forms and these by 3 linear forms, well, unfortunately, I get a coincidence. If I multiply this by B2 and this by B1, then I get the same thing. That's a syzygy, right? A relation between these two things. But in any case, it prevents me from getting 6 independent cubics. I only get 5 independent cubics. So I need at least one more cubic generator for this ideal. And it's not very hard to see that there are, to draw another cubic and to see that we then do impose independent conditions. Let me draw a cubic. Well, you can certainly have a cubic function going through 3 points on the line. And why shouldn't it go through this point too? Maybe I should have drawn this point somewhere else in order to make it easy to draw. But let's see. So the cubic might go like this, right, on its way to infinity. That's not a cubic. One extra loop in the snake. There we are. There's a cubic. Not a very cubic, but oh well. So there are the equations, and we can write down syzygies explicitly. So let's call the cubic C. By the way, notice that C goes through this point, and this point is actually cut out by B1 and B2. It's the intersection of B1 and B2. So C is a linear combination of B1 and B2. Let's write it as F1 B1 plus F2 B2. Okay? So the F's are quadratic forms. And now the 3 equations, as I've written them down, well, we have 2 equations of degree 2 plus 1 equation of degree 3. So the matrix here is A times B1, A times B2, C. And now C I could rewrite as I said, as F1. Well, let's just think of it as C. What are the relations on that? Well, we saw one syzygy already, namely B2 times AB1 is B1 times AB2. So I can put a B2 minus B1 0 here, and that will be a relation on those 3. What about others? Well, I can't write C as a linear combination of AB1 and AB2, but I could write A times C as a linear combination. So there'll be a relation with an A down here, or minus A maybe, and an F1 and F2 above it. So I can put F1, F2, and minus A, and there's another relation. And in fact, and again, this is something that maybe Jessica will tell you about tomorrow, that's all the relations. So there's a relation which consists of linear forms on quadrics. So that's a relation of total degree minus 3. And there's a relation which multiplies those 2 quadrics by quadrics. So that's a relation of degree 4. And that's the end of the resolution. So the Betty diagram of this will look like this. Here's the 1 for the generator of S. Then for the 2 generators in degree 2, remember we step back 1 and down 1, so we have a 2 here, but there's now also a 1 there for the cubic. And stepping back 1 further, there's a cubic that's sort of degree 1 back from the quadrics there, and a quartic that's 1 there. So there's the Betty diagram for this resolution, and you can see that it differs from that Betti diagram. Well, the only other thing I want you to notice before I stop is that the alternating sum of this diagonal is 0, which is the same as the alternating sum of this diagonal, and the alternating sums of all the diagonals, in fact, are the same in these two diagrams. That's a general fact, and those alternating sums are exactly the data of the Hilbert function. Perhaps we'll come back to that next time. Anyway, this is the first example of a flat family. That's what you're seeing here, a flat family of rings where the different kinds, the geometrically different kinds, are distinguished by their graded Betti numbers. So, thank you very much. Questions? I'm happy to answer. The experts.
I haven't quite formulated this question yet, but if you understand what D points into play.
Yes.
I'd like to know whether the graded Betti numbers distinguish everything you would think of the form, how many points lie on a curve, the Q points lie on a curve of degree R. So
I don't think so, but they take a... thank you. So the question was, how much information do we get for D points in the plane? Well, of course, Rebecca is going to tell you all about that tomorrow, but to say something in slightly in advance, it only captures some of the information that Robin is after. Robin asked, so if you take D points in the plane, then you could make a huge matrix of numbers by looking at the maximum number of those points that lie on a curve of degree E, right? So there's some big collection of invariants there. How many of them are captured in the graded Betti numbers? Answer, some. Unfortunately, it's not complete, but certainly you can tell, for example, what the lowest degree of a curve that passes through all the points is, right? That's the first information of the graded Betti numbers, but that's already in the Hilbert function. And then this shows that you get a little more information than that, and it's somewhere in between.
I have an example of your sleeve of where the Betti numbers are the same, but the geometry is different.
I think there's one in my manuscript, but I don't have it in my sleeve. So there is a manuscript. It looks like this. There's a version on my web page now. There will be a better version on my web page this afternoon because I have a more corrected version than what I have here. This is the most corrected version. I'll put it in the library right now. But it's in progress. And the title is The Geometry of Syzygies. It will be a Springer graduate text sometime around next spring, I would guess. Any other questions? Yes.
Yes. Did you consider the generating function associated with numbers?
Sure. So the Hilbert function, you mean of the Hilbert function?
Well, instead of looking at these polynomials, there's something that's a polynomial function.
Right.
Consider a rational function expression.
Of course. So the other way to write this, and it's the right way if you look at polynomial rings where the generators are in different degrees, is as a generating function. And then exactly the same arguments show that the generating function that you make out of this, so summation hm of d t to the d, is a rational function with a special denominator. In this case that I'm looking at, it'll be 1 over, I guess it's a power series in t, 1 minus t to the r, and then there's a numerator, which can be various things. This is a whole interesting subject, what the generating function can look like, and lots is known in this direction. In some sense, all Hilbert functions are of homomorphic images of a polynomial ring are classified by Macaulay. Macaulay says which are possible, and so in some sense this collection of generating functions is known. Mark Heyman, in his early career, made a specialty of knowing which functions are generating functions of this type, and it's quite beautiful. Any other questions?